Hello and welcome to the I Think Biology NPTEL course. This week we are discussing biology and climate change. In the first lecture on this topic, I introduced the concept of the planetary boundaries. The planetary boundaries are 9 processes that regulate the stability and resilience of the Earth system. Climate change is just one of these boundaries. And as you can see in the figure, from 2009 to 2023, we are now in the position where 6 of these boundaries have been crossed, which means we are entering a zone of great risk and uncertainty. And maintaining the planetary boundaries is important because if we remain within these boundaries, then humanity, or basically life on Earth, can continue to develop and prosper for years to come. The other framework I introduced was that of the Sustainable Development Goals. So how are we to remain within these 9 planetary boundaries and continue to develop as a human society? So the SDGs provide us with a pathway to do that. And the SDGs are 17 interlinked objectives, and they serve as a blueprint for peace and prosperity for people and the planet. And they were adopted during a UN meeting in 2015, and India is also a signatory to the SDGs and achieving the SDGs. And this model of the SDGs makes it very clear that the biosphere, or maintaining the biosphere, which is basically life on land or life on earth, fresh water, maintaining those systems are key for human society to develop and achieving societal goals like an end to hunger or an end to poverty. And from there, we can move on to a thriving economy. So this is a good way of looking at the whole picture of the SDGs. Now let's look at climate change in more detail. But before we do so, let's talk a little bit about terminology. We hear these words like global warming and climate change, and they're used pretty interchangeably, but they mean slightly different things. So global warming refers to the rise in global temperatures, which is mainly due to the increasing concentration of greenhouse gases in the atmosphere from the burning of fossil fuels. Climate change is more of an umbrella term, and it refers to the increasing changes that we are now observing to climate or to measures of climate over a longer period of time. And these measures are things like increased rainfall or changes to temperature and wind patterns. But because the Earth's temperature tends to be a central determinant of its climate, we talk about climate change and global warming interchangeably. I'm now going to talk about global warming, and then we will come to climate change. So global warming has been known as a problem for over 100 years. So this is a news report from 1912, and it says, the furnaces of the world are now burning about 2 billion tons of coal a year. When this is burned, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. This tends to make the air a more effective blanket for the Earth and to raise its temperature. So in a very brief and precise fashion, it has laid out the problem and its causes. So now let's look at some of the data about global warming. And these come from IPCC reports. The IPCC is the Intergovernmental Panel on Climate Change, which is a global scientific body which advises the UN and governments around the world about climate change. So the graph on the left plots the Earth's global surface temperature over the last 2,000 years. And you can see that it stays mainly flat or horizontal. And in fact, starting around 1500s, there's even a small dip, which is known as the mini ice age. But then starting around 1850, we start to see an upward trend with increased spike in the 20th century. And this warming has not been seen over the last 100,000 years. And the warming is on the order of about 1 degree centigrade. The graph on the right shows us an expanded view of the time period between 1850 and 2020. So we can see this warming trend more clearly. And then overlaid on the data are simulations, and these are done in two ways. A simulation using just natural factors to account for the warming, which is the line shown in green, and a simulation which takes into account human factors along with the natural factors to account for the warming. And we see that only when we take into account human factors does the simulation fit the data, indicating that it is indeed human activity which is responsible for the warming trend which is now being seen. This image shows us the same pattern except on a global scale. So here we are plotting global surface temperatures as an average for 2011 to 2021 against a baseline of 1956 to 1976. And over most of the world, we see a warming trend. And in fact, a lot of the warming is seen towards the poles in the Arctic, which has seen a temperature change of around 2 degrees centigrade, which is indeed quite a lot and very worrisome. So what are the measures that the IPCC uses to track climate change? And shown here are 4 such measures. So the graph in A is for global surface temperature, which I've already spoken about. The graph in B tracks Arctic sea ice change in units of million kilometers square. The graph in C is for ocean surface pH. So this is in units of pH, which is a measure of acidity. And the graph in D is the mean sea level change in meters. And the data is plotted from 1950 onwards to 2015. And so the lines in gray are the actual data. And then the colored lines are simulations which the IPCC has done, taking into account different socio-economic pathways that the world can use to develop towards 2100. So I will come to what these SSPs are later on in the lecture. But for now, let's just concentrate on the gray lines. So I have already spoken about the global surface temperature and how we have seen a 1 degree rise as compared to 1850 to 1900. Now coming to the graph in B, we see that there is a decrease in the Arctic sea ice area from approximately 6 million kilometers squares starting in 1950 to about 4 million kilometers squares by 2015. Similarly, for pH, the graph in C, we can see that there is a decrease in pH. And while the decrease may not seem like much, when in the lab we are doing these titrations and acid-base titrations and we are looking at changes of pH of 2 to 3 units, this may not seem like a lot, but it is really quite drastic for the ocean's ecosystem and all the marine organisms that live in the Earth's oceans, because increasing acidity can spell disaster for a lot of organisms that use calcium carbonate to create their exoskeleton. Finally, we come to the mean sea level change shown in D. And here again, you see an upward trend of about approximately a quarter meter. And again, this may not seem like a lot, but if you consider the large amount of humanity that lives on low-lying islands or coral atolls or next to a coastline, this change can spell drastic consequences for them. Then coming to the infographic, which is shown on the right, this shows you the kind of data that the IPCC uses to generate its reports. So it relies on paleo records or fossil records. So basically these are looking at ice core data or marine fossils to measure the amount of carbon dioxide in them. Then they look at imaging data from satellite to track sea ice changes, or they have a global network of floats which can track pH changes or the sea level change. And finally, they also use simulations and theory. So we now have built up a very good understanding of the Earth's climate over the last 100 years. And so using known physical laws, we can simulate the changes to the climate and try and fit it to the observed data. So the IPCC really uses a variety of methods to arrive at its recommendations. So moving on from looking at changes to climate to the causes of global warming. And global warming is caused due to an accumulation of greenhouse gases in the atmosphere. And the primary greenhouse gas here is carbon dioxide. And the graph on the left shows you the concentration of carbon dioxide in the atmosphere. And this is a continuous measurement which has been kept at an observatory in Hawaii since 1958. It was started by a scientist named Charles Keeling, and this is now known as the Keeling curve. And you can see that there is a continuous upward trend starting at approximately 220 parts per million in 1958 to that over 400 parts per million by 2020. So carbon dioxide is now accumulating in the atmosphere at a very rapid rate. One interesting thing about this curve is the sawtooth pattern. And I have asked a question there, why does this curve have this kind of a pattern? So as students of biology, we should think about that. The graph on the right shows you more historical data. So this is tracking carbon dioxide concentrations in the atmosphere over the last 1,000 years. And you can see that they remain mainly flat or they do not exhibit much change. But then starting around 1800, we start to see an upward trend or an increase in the carbon dioxide present in the atmosphere, and it really starting to spike in the middle of the 20th century. So what does the accumulation of greenhouse gases in the atmosphere and the associated warming do to the Earth's climate? So for here we have to consider the Earth's energy budget. And under normal circumstances, you would have a stable climate where you have a certain amount of solar energy coming in. Some of it will be absorbed and then most of it will be reflected out. But in today's scenario, because you have this blanket over the Earth's surface in the form of these greenhouse gases, there is less energy going out, so it is remaining trapped. And so where is that energy going? And looks like most of that excess energy is being absorbed by the Earth's oceans, leading to their warming. This graph shows us the sources of these global warming in greater detail. Radiative forcing basically refers to this Earth's energy balance, which I spoke about on the earlier slide. And radiative forcing is measured in watts per meter square. So we can think of it as energy incident upon unit area. And so the different sources that contribute to an increase in radiative forcing, which are basically all the horizontal bars going towards the right and shown in red, are greenhouse gases. And greenhouse gases are carbon dioxide, methane, nitrous oxides, and halogenated gases. So they all contribute to the warming. There are certain effects which can contribute to cooling. So these are the bars shown in blue, and these are basically aerosols. So we can think of them as particulate matter in the air or in the atmosphere, and they have a cooling effect due to blocking of this incoming solar radiation. But if we add up all these sources and their effects, we see at the bottom that overall there is a net warming trend in the radiative forcing. And then if you look at the columns to the right, you can see that for each source, you're given what is the extent of its scale. So carbon dioxide or greenhouse gases, basically the effect is global. And then some of these other parameters might have more local or continental effects. For instance, like aerosols might be more localized on a continent or even over a country. The last column refers to LOSU, which means level of scientific understanding. So for each of these radiative forcing components, the IPCC has given us a subjective parameter of what is the current level of scientific understanding of its contribution to the overall radiative forcing. And we can see for greenhouse gases, the level of scientific understanding is high. This shows us the same data, but except now it is plotted for temperature instead of radiative forcing, so it's in degrees centigrade. So the graph on the left shows us that overall there has been a warming trend of approximately 1 degree centigrade. And then the graph on the right in B and C shows us the various contributors to this warming. And you can see that greenhouse gases in the form of carbon dioxide, methane, nitrous oxides, and halogenated gases shown in the graph in C are all contributors to warming, whereas you can have aerosols which can come from a variety of sources which can contribute to some cooling. So now let's look at the major greenhouse gas, which is carbon dioxide, and its level of emissions globally. And here the graph shows us the change in global CO2 emissions from 1850 to 2021. And you can see that there is a constant upward trend to the amount of CO2 being emitted into the atmosphere. And one thing that you should note here is the numbers shown on the y-axis. So the major contributor to CO2 emissions are fossil fuels. And currently, we are emitting about 40 billion tons of CO2 into the atmosphere per year. And so as students of science, we need to have certain numbers at our fingertips. And this is one number that you should keep in your head. So then moving on to who are the emitters of these greenhouse gases. So there are two graphs shown here, present day emitters, and the data are for 2017. And then historical emitters, where the data is clubbed from 1751 to 2017. And if you look at the graph on the left, the different colors refer to different continents. So Asia is shown in red, North America in green, Europe in yellow, and so on. And here, if you look at Asia under present day emitters, China is a major emitter and it contributes about 27% of global emissions. If you look at the US, it contributes about 15% of global emissions. And if you look at the EU as a whole, so EU 28, it contributes approximately 10% of global emissions. And in 2017, India contributed about 6.8% to global emissions. And you will notice that in blue is shown the continent of Africa, and the whole continent contributed only 3.7% to global emissions. If you look at the historical graph shown on the right, so who has contributed most to global CO2 emissions, we can see that North America and especially the USA has contributed about 25% or a quarter of all global cumulative emissions since 1751. China has contributed about 12.7%, and India has historically contributed only 3%. This graph shows us the changes to the share of global CO2 emissions as a function of time for various countries. So the line in pink or purple is for the United Kingdom, and it shows us that it started out by contributing a majority of the share to global CO2 emissions in 1750 because it was an early pioneer in the Industrial Revolution. And then you start to see its share decreasing as the years progress. And in 1889, you see an inflection point where the US overtakes the UK in share of CO2 emissions. So this one graph is actually a good historical document if you want to look at human development since the Industrial Revolution. And then starting, say, in the 1980s, you see a large upward trend for China, which is shown by the line in light blue. So just summarizing the historical data, the United States has emitted more CO2 than any other country to date at around 400 billion tons and is responsible for 25% of historical emissions. The EU 28 is also a large historical contributor at 22%. And many of the large emitters today, such as India or Brazil, are not large contributors in a historical context. So this is a very problematic issue because to figure out who is responsible for climate change, because once you decide responsibility, then you know that who is responsible the most for fixing it. But there are different ways of looking at it. So one is this lens that I showed you of the historical perspective versus the present day. You can also do a sector-wise gradation. And so which are the major industries that contribute to fossil fuel emissions? They are basically the fossil fuel industry, of which electricity generation is a major cause. Then cement and steel industries are major contributors to CO2 emissions. You can look at it from the lens of lifestyle. So basically, people with high incomes are the major contributors to CO2 emissions in the present day. And so even within India, there is a very large disparity with people in the top 1% contributing out of proportion to the population, to the carbon footprint of India. You can also look at it from the perspective of producers and consumers. So here is a question for you. If a car is produced in China and driven in the US, who is responsible for its emissions? Finally, a good way of looking at it is in the context of what is called as CBDR, common but differentiated responsibilities. And this phrase was actually put in to the Rio Declaration during the Rio Earth Summit of 1992. And India played a large role in putting in this language. So what this means is that we acknowledge that global warming and climate change are serious problems, and it's a problem common to humanity. But everybody has a different level of responsibility for fixing it. And so again, we can look at it using different lenses to figure out what is the level of responsibility of each person or each sector or each producer or consumer. I will just show you one more graph related to this. This graph looks a bit complicated, but it's not. The x-axis is plotting the population country-wise, and this x-axis has now been bent to form a three-quarter circle around the Earth shown in the center. The y-axis shows us the carbon dioxide emissions per capita in terms of tons per year. So basically, you take the total CO2 emissions of a country and you divide it by its population, so you get the per capita emissions. And you can see that there are certain countries in the Middle East which are amongst the top in terms of per capita emissions, and they're close to 20 tons per year. The US has a very large per capita footprint at almost 15 tons per year. China is at 7.1 tons per capita. India is relatively low at 7.1 tons per capita. So again, if you look at China, you might think, okay, it has a very large footprint, but if you divide it by the population of China, which corresponds to a very large percentage of humanity, then it is below the global average. So this one graph allows us to look at the problem in a different way. So this plots CO2 emissions along a timeline, and we can see that it has been divided into two different areas. So CO2 emissions before 1990, and they have been added up, and CO2 emissions in the 30-year period, approximate 30-year period from 1991 to 2019. And we can see in the last 30 years, we have emitted more than 50% of all the CO2 which has presently accumulated in the atmosphere. So if there is one piece of data or one information that I would like you to take away from this lecture, it is this, that in the last 30 years, we have emitted more than 50% of all the CO2 which is now accumulated in the atmosphere. So what are we doing about all this? And the major player in telling us what we should be doing is the UNFCCC, which is the United Nations Framework Convention on Climate Change. So this was a historic document which the countries of the world were signatories to. So once you sign on to the UNFCCC, you become you become a party to the conference. And starting in 1995, you had a conference of these parties. And then moving on every year since, we have had a COP. And at every COP, different targets are discussed. Different things like funding is discussed or fixing responsibility is discussed. And the COP always uses the IPCC reports as a basis for making any decisions. And so the IPCC has so far released 6 reports, which are called as assessment reports, AR. And the last report was in 2020. It was published in 2021. So the COPs really are the global forum on which we decide action against for the climate crisis, starting in 1992 when the UNFCCC was signed. Since then, we've had COPs, and each COP has had its own flavor. And this graph shows us some of the highlights, where in 1997, there was a pledge to reduce global emissions by half, and it was a very encouraging COP. To the low of 2009 in Copenhagen, when the US was expected to make a very historic announcement, which it didn't. And then again to the last big inflection, which is in 2015, where we finally had the Paris Agreement, where 195 countries and the EU pledged to limit global warming to within 2 degrees centigrade and preferably to less than 1.5 degrees centigrade. So in line with the Paris Agreement, if we are to maintain global warming to less than 2 degrees centigrade or preferably to less than 1.5 degrees centigrade, then this is the trajectory for CO2 emissions that we should be following. The y-axis shows us gigatons of CO2 equivalent, which means it is clubbing together all the greenhouse gases and then plotting it as a cumulative CO2 total. So you can see that currently we are at approximately 50 billion tons of CO2 equivalent, and that needs to be reduced to about 20 billion tons per equivalent by the next 7 years, by 2030, in order for us to meet the target of keeping warming within 1.5 degrees centigrade. So India is also a signatory to the Paris Agreement. And so if you are a signatory, then you have an NDC, the Nationally Determined Contribution, which is basically what are you pledging in order to counter climate change. And so India has made very ambitious targets, and this is India's updated NDC. So the first target is we have affirmed to reduce our emissions intensity of its GDP by 45% by 2030 against a baseline of 2005 level. So what this basically means is that if you're doing any kind of economic activity, say for instance, you're producing cars, so what was the level of CO2 you emitted in order to produce 1,000 cars? And against that level, we are saying we will reduce that level by 45% in order to produce those same 1,000 cars by 2030. The second target is that of renewable energy. So we are pledging to achieve a 50% cumulative electric power installed capacity from non-fossil fuel based energy sources by 2030. And the third one is that we will create a carbon sink, which is basically using forests to sequester carbon, and the sink will be to the level of 2.5 to 3 billion tons of CO2 equivalent. And this will be through various afforestation and restoration measures. So what is to be done about climate change, there are basically two actions that one can take. One is that of mitigation and the other one is that of adaptation. So mitigation is basically what are the actions you can take in order to avoid or drastically reduce greenhouse gas emissions. And adaptations is basically assuming that climate change is real, it is affecting us right now. So what are its current or future consequences and what can we do in order to adjust to these changes in the climate? And so there are a variety of measures that one can think of. For instance, renewable energy is a big mitigation measure that you can take in order to reduce greenhouse gas emissions. And of course, I should mention that mitigation measures and adaptation measures are not independent of each other and in fact can in many ways can intersect with each other. So how do you achieve mitigation and adaptation? And that depends on what is your pathway to development. And so we are coming back to these SSPs, which I spoke of earlier, the shared socio-economic pathways. And these are basically pathways of development which the IPCC has used in order to simulate what will be the rise in global temperatures. So SSP1 takes the most conservative pathway of development. It's that of assuming sustainability or taking the green road, as it says. And so here you would have the lowest challenge for mitigation, which means you would do perhaps a drastic change in your electricity generation or your transportation system in order to reduce carbon dioxide emissions. You would also have low challenges to adaptation, things like a heat action plan or finance measures to farmers against drought measures. Whereas SSP5 assumes that you're kind of taking the standard development pathway, which is energy intensive and it is fossil fueled development. So that's called taking the highway, which means we will reach a certain level of economic prosperity and then we will make changes which are necessary for mitigation or adaptation. So what are the major categories where you can do mitigation? And this is shown here on this graph. It's a bit complicated, but perhaps I can break it down. So the first major category in which we need to do mitigation is that of energy generation. And here we need to do an adoption of renewable energy sources such as wind energy or solar energy. So the horizontal bars tell us what is the potential contribution to a reduction in gigatons of CO2 equivalent per year if we go all out in terms of adoption of wind energy or solar energy. And so, for instance, you can expect a potential contribution of a reduction of 4 billion tons of CO2 emissions if we do a complete adoption of wind energy. And the colors of the bar refer to what is the expected cost in order to make this change. So going from a net reduction of 2 gigatons per year of carbon dioxide to 4, there is a large increase in the cost. That's what the graph is telling us. The second category is called AFOLU, which stands for agriculture, forestry, and other land use. So basically, agriculture can be used for carbon sequestration, or you can do things like ecosystem restoration, afforestation, which will again be a carbon sink. And so they have a large potential for mitigation, but what these graphs are saying are that the cost associated with that might be quite high. But we must remember that this is calculating the cost in economic terms. The cost in social terms or cultural terms might have greater benefits than just the economic cost. The other category for mitigation is that of building construction. So because we use a huge amount of steel and concrete in building construction and infrastructure development around the world, it's a major category in which we need to do climate mitigation. So again, there are various categories here. For instance, we can have things like new buildings which are green buildings, or we can have on-site energy generation, so a decentralized model of energy generation. The next category is that of transport, followed by industry. So as you can see, this graph shows us all the major categories of human activity and what are the areas in which we can do mitigation and what is the level to which we can expect mitigation if we do an adoption of all these various measures. Then coming to climate adaptation. So adaptation we can do in two ways. One is that we give governments money or people money or certain communities money so that they can take actions that reduces the risk and decreases harm from present climate hazards or future climate hazards. The other one is quite simple. It is called nature-based solutions. So what are the actions you can take to protect, manage, and restore ecosystems? And this can have multiple benefits, not just for climate. And so the adaptation measures you can do is for preventing floods, ensuring that your freshwater supply is protected in many different ways. You have a heat adaptation plan, say for cities in terms of cooling systems. You make changes to your food systems in terms of heat resistant strains. You have disaster management systems for early warning, quick response, and you can do restoration, which I already spoke about. And you can see that we can have a variety of adaptation options depending on the context. And there are two major categories here. What are the adaptation measures you will need in rural areas and adaptation measures in urban areas? And because you're seeing a large urbanization trend, how do you manage your present city so that you have different adaptation measures against climate change and warming? For instance, you can see that different cities around the world have different measures. So sea walls to prevent sea ingress, or things like a sponge city in China, which will act counter flooding, or you can have a heat action plan, which the city of Ahmedabad has, or you can have coastal regulation in Mumbai. So adaptation is basically a measure against the extreme weather events which are increasingly being seen around the world. And you can use this tracker to figure out what different weather events are being seen around the world and what are the trends being seen for them. So what is the situation in India? What are the effects of climate change being felt in India? So shown here is a comparison of the changes in temperature seen between 2008 to 2018 against a baseline of 1950 to 1980. And the grids are a grid of 1 degree by 1 degree. And this is based on data provided by the Indian Meteorological Department. So you can see that the grids in purple mean there has been a warming trend in those areas. So parts of Rajasthan and Gujarat, parts of South India in Tamil Nadu have seen a warming trend, whereas certain parts in the Gangetic Plains have seen a small cooling trend. This could be due to the presence of aerosols from air pollution in the atmosphere, which block solar radiation, basically cooling the land surface. But overall, we can see that many parts of the country have experienced a warming trend. Then this map shows you the risk or vulnerability of rural areas to climate change, because agriculture is the mainstay of people's livelihoods and our economy. And so this map shows us a district-wise risk assessment to climate change. And there were three measures used. One is what is the sensitivity of a particular location to changes in the weather, what is its exposure, so what is the level of change basically, and what is its adaptive capacity. So adaptive capacity could mean things like administrative, how good is the administration, or what are the measures being taken, is there finance available, things like that. And so as you can see, parts of Rajasthan, Gujarat, large parts of Maharashtra and Karnataka, districts in there are at extreme risk to climate change, whereas certain coastal areas are less vulnerable to climate change. Finally, this map shows us the vulnerability to flooding. So we are already witnessing severe storms like cyclones, and we are seeing sea ingress into low-lying areas. And because India has a very large coastline, what is the risk level certain areas in the country have to these changes? And so the inset on the blue shows us that areas which are marked in blue are particularly vulnerable to things like sea level ingress or exposure to storms. So indeed, India is going to be heavily affected by climate change. So I hope you have had a good introduction to climate change. In the third lecture in this series, we will look at what are the effects of climate change on the biosphere, and we will do this at 3 different scales. I will see you in that lecture. Thank you.